So, good morning, everybody, and welcome to 307 during the summer with myself. I am Dr. Alexander Lopez. I'm an assistant professor here in the chemical engineering department. I know some of you have taken this course previously with Dr. O'Haver and are taking it now. I know some other of you are taking it for the first time, and so this course will kind of work for essentially irregardless of when you've taken the class or how familiar you are with the actual course materials. And so before I kind of start jumping into stuff, I want to give you all just kind of a quick overview. The main thing being, this course covers major concepts centralized around process material balances. In the introductory course for chemical engineers, we touched base a little bit on it, but this is the major course where we kind of get into the specifics surrounding material balances as they apply to chemical processes and other things in general. And the way I see them, it's really just accounting for engineering. If you can get the key principles around material balances, as well as the problem solving strategies and how you tackle these problems, I think you'll do well. The other major component in terms of this class is just ensuring that you dedicate enough time to going through the textbook, looking through notes, taking your own notes, working through homework problems, getting through the quizzes, interacting with myself, and just staying engaged. Because in my experience, the more students are engaged, the more time, effort, and energy you're putting into something, the higher your chances of success. And so my goal for you all this, I guess, mini semester is to do what I can to keep you all engaged with this course and its content to ensure that you learn the skills and the knowledge necessary to do well in this course as well as in the courses that follow. All right, so with that, I'm going to go ahead and jump in and let's talk briefly on the syllabus. So I've already posted the syllabus, the schedule, as well as quite a bit of content for chapter 4 and initial homeworks in Blackboard. But I want to take some time to go over just some of the general course structure to ensure we're all on the same page. As I said, this is 307, Chemical Process Principles. It will take place during this first summer semester, which is between now and the end of June. I believe the final exam is about the 23rd, 24th of June, which is, it's further down. Big thing here is you really need the textbook in order to do everything that it's required in terms of getting that information, because this is a really good textbook. It's elementary process principles, elementary principles of chemical processes. You can have the 3rd or 4th edition. I'm not really picky about editions. You know, the content is largely the same. So long as you have one copy that you can access, either, you know, a physical copy or a digital copy, that's really going to help you as you move through this course. A couple references that could help you in addition to the Felder and Rousseau text is Himmelblau and Riggs, Basic Principles and Calculations in Chemical Engineering. It's essentially covers the same material, just in a different manner, which helps. You know, I find some students have certain learning styles that links up with some textbooks versus others, so I always like to provide alternates, just in case you're having trouble digesting content from one source, you have multiple other sources. I also really strongly encourage you to utilize the learnchemie.com resource. They have a large number of videos, tutorials, and problems associated with material balances and chemical process principles that can really help to reinforce the material content and skills to be gained from this course. So I really encourage you to, when you can, engage with that learnchemie.com website to really, get more practice and, like I said, increase your engagement in the course. In terms of the classroom, as you see, we're fully online this semester, so everything's going to be on Blackboard through email, and then I'm going to host these lectures, which are optional, but I think they're good ways to interact with myself. In terms of office hours, I will hold office hours in the afternoons, Monday through Friday, on the days which are considered class days. From about 2 p.m. to 4 p.m., I will send a link after class with that office hour Zoom link. So you can, and I'll just kind of be working on other things, and you can drop in, ask a question. If you have issues with homework or trouble, we can kind of talk things. I can help you out. That's what it's going to be there for. So feel free to come with questions. I'm going to probably try to emphasize more the homework type questions in the office hours versus the lectures, just because I don't we can kind of get down some homework rabbit trails, so I don't want to do that when we do some of the lecture material. But beyond that, don't hesitate to email me. Just be a little patient in terms of me responding. Sometimes when I get an email at 8:30 at night, I may not respond till the morning just because it's 8:30 at night. So please be patient with that. But I will answer your emails, and if you feel like it's been a little long, you can feel free to send me another email. It's not going to bother me in the slightest. But I am here for you guys, and I want to make sure that you all do well and that your questions are answered as we work through this course together. In terms of the lecture objectives, you guys can read that if you'd like, but the really big thing, which is here kind of at the bottom in these bullets, is being able to develop labeled diagrams to give context to process descriptions, as well as applying engineering concepts to formulate effective solutions using appropriate problem-solving strategies. We'll talk about that, later when I get into some of this lecture material. That doesn't mean, if the goal is to find concentration of a stream, I don't want you to just scribble some calculations on your homework solution and then circle this as a concentration. We need to be a little more organized, a little more thorough, because a big aspect of engineering is communication, and we want to be able to ensure that anyone that looks at a homework solution knows what the heck it's actually supposed to be, what's the context around it, what is it trying to show, and is it effectively showing it, not just the answer's 12, let's move on, because that's not effective in our communication. And so we want to be able to be a little better about how we do things in this class. And then, of course, looking at solving steady state mass balance, material balance problems for various systems. We have a whole lot of systems to discuss. Things with and without chemical reaction, with and without recycle, bypass, purge streams. There's a whole lot we can talk about. Then we're going to start looking at multi-component systems a little bit, considering ideal gases and non-ideal gases. Luckily, we're just going to look at some what I consider base level non-idealities. The more complex stuff that's where the advanced thermo comes in. And really just, like I said, focusing on those problem-solving skills and being able to take complex problems, break them out a little bit, and provide an effective solution that is easily to read, very well communicated. In terms of topics, these are the topics that we're going to cover. It's going to majorly consist of chapters 4, 5, and 6 in the Felder and Rousseau text. And so that's going to be the bulk of this course. with real strong emphasis on chapters 4 and chapter 6. Chapter 5 is a little short. It almost feels like an introduction to chapter 6. But in terms of what are the chapters do I need to be reading, those are going to be the ones, and we'll talk about that a little bit more here in a second. And as always, as we're accredited by ABET, we like to kind of state what the objectives that we focus on in this course, which is solving problems and applying effective design principles to produce reasonable solutions. All right, so homework. So the homework's going to be due about every 3 to 4 days. The only one that's a little different is there's one due Friday in 2 days, which is over some review material. It's just a few problems, making sure we're all comfortable with the material from chapter 3 of Felder and Rousseau, which we'll talk about today. But everything's going to be due in Blackboard. And since I know some of you have work obligations and things, I had originally thought about having things due at 5, but I don't think that really works for people that work, and so I'm just pushing everything. It'll be due at 11, midnight with an 11:59 cutoff. That way, for those of you that are a little more active and engaged later in night, you have the opportunity to do that and ensure you get it in on time. So everything's just going to be due by 11:59 p.m. on Blackboard. I really like submitting that homework as a single PDF. It makes it so it's a lot easier to grade in the system. The big issue that I've seen in the past is when people try to do things on paper, which I'm comfortable with, but then you take pictures, and then I've got 12 image files in one submission, and it's really a pain for the grader to go through that. So if you can use a little app to scan whatever you do by hand, I'm really, I strongly encourage you to do all by hand instead of just on the computer. You can use a scanner app. I know the seniors I've worked with use like a CAM scanner app to do scans of handwritten solutions, and it auto formats it to PDF. That's a good way to get it all compiled as a single PDF and submit it to Blackboard. In terms of late homework, my policy is I'll accept one late homework with no penalty because I understand life happens. But after that one essentially pass, homework just won't be accepted. And so I really strongly encourage you, don't use your pass in the beginning just because, it's a nice day or you just don't feel like it. I encourage students, use it when you need it, because if you use it when you don't, a week later, you're going to need it and you're not going to have it. And so, like I said, and be sure to get the homework in. There isn't a whole lot, and they're worth quite a bit in this course. As we can see in this grading scheme, we have homeworks, quizzes, a midterm and a final, and a case study, which I'll talk about here in a little bit. And so the homework is worth 25% of your grade. And then I'll have some short quizzes, which I'll talk about. That'll be worth about 15, which will emphasize just the key concepts in the course, as well as the textbook reading. Then you'll have a midterm in the midpoint of this semester, and then of course a final. And then a case study as a cumulative project that you'll be working on throughout the course, little by little. In terms of academic dishonesty, I just go by the university's policy. Just don't cheat. It doesn't help you. Any questions? I've been kind of rambling for a little bit, so I'll go ahead and stop. No? Okay. I'll keep going. All right, so the case study is going to be essentially a mini project. It will be essentially a pretty complex material balance that you'll have to dissect. And you can complete it by yourself, or you can complete it in pairs, if you so choose. I leave that to you to decide, and to you to let me know if you decide to work in pairs, who you plan to work with. But it's just a good way to bring all the main concepts for this class together in one little project. That is already up on Blackboard. I'll talk about it here in a minute, but I do want to let you know it is available. Grading scale, just use the pretty standard plus minus scale that we have, where 93 and above is an A, 90 to 93 is an A minus, and things like that. There's the grading scale. Quizzes. All right, it says they're going to be approximately 2 quizzes per week. That may or may not always be the case. It'll be about every 4 or 5 days. You'll have to check the schedule in Blackboard to see when they're due. I'll show you the schedule as soon as we're done with this. But the quizzes is going to be on Blackboard, and they're going to be timed actually at about, I think I put 20 minutes, not 15 minutes. So I'll fix the syllabus and re-upload it here in a little bit. But it's, I strongly encourage you get through the textbook sections that the quiz states that it covers. Make sure you're comfortable with the material before you do it, because you have to do it in one sitting. And as soon as you click it, the timer starts. And I've kind of written them assuming you have access to your notes and your book and everything, because I can't not keep you access to that, because that every proctor service that I've had colleagues use have ended up in miserable failures. And so just make sure you're ready before you engage with it, because if you try to do it and it screws up, then I'll have to figure something out, and I don't know what we're gonna have to do. But well, I guess we'll get to there when we get there. But like I said, just make sure you're prepared to do those quizzes. They're gonna be about 5 problems in each quiz, which gives you about 4 minutes per problem. And they're going to be, I think thus far they've simply just been multiple choice type, which is useful, but at the same time it's kind of an all or nothing kind of thing. In terms of the exams, we have 2 exams, a midterm and a final. The midterms are going to, and final is going to take place during these times. The way it's going to work is I'm going to send out the exam at 11 and noon respectively, and then I'm going to give you that time, and they'll be due in Blackboard by that cutoff time, 3 p.m. and 3:45. I like to send them out early and put my exams in during the syllabus day 1. Makes it easy, especially for these kinds of classes that are abridged. So that if you have work things or other issues, you can try to get out of them or around them. But I'll try to work with you if you have issues. I've already had one student that was in another class that wanted to book, and I've been working with that student to find another time for them or adjust it a little bit. So I will work with you, but I like to let it, make it known so you kind of have, a good heads up. Like I said, I already told you about the office hours. It'll be about from 2 to 4 every day. And last but not least, if you have a disability accommodation, I'd be more than happy to work with you. I want to make sure everyone in my class has the opportunity to learn and engage. I just ask that you go through the proper channels by contacting the Office of Student Disability Services to make sure all the proper paperwork that needs to be done is done, so that we can come at it from the right angle. My only request in that regard is, if you need accommodation, please let me know sooner rather than later, because I'm not a huge fan of someone requesting extra time on an exam the day before an exam. That creates more of an issue is if you tell me, like, in a few days or a week before, that I can be a lot more accommodating. So any questions on the syllabus thus far? No? Okay. So let's switch gears and talk briefly on the course schedule. So I've created this little calendar. It's available on Blackboard next to the syllabus. So you can get a good snapshot of essentially the course from beginning to end. And I've kind of broken it out so that so long as you stay on track, reading the sections that I've identified, focusing on the topics, and ensuring that you understand what's due and what's assigned on what day, you won't fall behind and you won't have issues getting things done on time. For example, today we're just doing some introductory stuff. I'm gonna have a brief lecture on reviewing material from chapter 3, focusing on chemical process variables. At the same time, the homework 1 is formally assigned. It will be due on Friday. And the case study is also available and assigned today, and it is due at the end of the course on June 22nd. But you can see very quickly how much we go through in this course. And there's that, about 200 pages worth of material, 3 chapters in this text. And so it's really easy to fall behind. And so, like I said, I just want to encourage you guys to stay engaged with it as much as you can on a daily basis. Attend these lectures when you can't. When you can't, try to review this on Blackboard so that you make sure you're staying on top of this and you don't get fall behind. It's like those chemistry courses. And, I remember OChem was one of those things. If you missed a day, you felt like you're a week behind. And that's kind of how it is, unfortunately, with summer classes. Since we're having to condense and cram everything into 1 month, which is usually 3.5, it becomes a little dense, a little hard to chew through. So consistency will really help you and serve you well. Was there any questions on the calendar course schedule that I released?
For the quizzes on like Saturday and Sunday is compressed into one column. Are the quizzes due on that Saturday or that Sunday?
That's a good question. I decided to just make them do that Sunday because since there's 2 days, I made it due on the last day.
Okay,
So,
thank you.
I think for now, quizzes are going to be due just for consistency basis on Sundays and Wednesdays. So you can see, quiz 1's this Sunday, quiz 2's next Wednesday, quiz 3, quiz 4. And I admit, all of this isn't already available. I didn't want to release the entirety of a course because I didn't want one person to just try to knock it out in a week, because that seemed a little much. But I think everything through, I think right before the midterm, I think SANS homework 5 quiz 4 is already up and going. If you want to get a little ahead, I'm okay with it. I just don't like it when somebody tries to, I don't know, run through the whole course in a week and then comes on office hours and being like, all right, I have a question about chapter 6. It just makes it a little hard to stay engaged with the class as a whole. But that is a very good question. Any other good questions? No? Okay. The next thing I want to touch base on before we kind of go through the review is the case study. Let me pull it up and then we'll talk on it. All right, so this is the case study that we prepared for this summer. And for those of you that are continuing, and second summer was 308, this will be the same case study that you will see in 308. Just with a little bit emphasis, you'll be focusing on energy balances and those calculations, while in this course, we're focusing on material balances. And so it's a nice ethylbenzene production process, yada, yada, yada. Here's the process flow diagram for it. It looks kind of messy, and that's because it is, because it's a very complex chemical process. But, looking at it, we can see that we have two reagents, benzene and ethylene, coming together, being heated before it enters a reactor to form the ethyl benzene, as well as a byproduct, diethylbenzene, which is separated in the form of a flash separator, two distillation columns. The flash gets all the essentially non-condensables that the condenser failed to work on, which is this E6O2. That goes out the process as fuel gas to be burned, someone else's problem. The distillation column, we have a recycle of benzene, where our product, ethylbenzene, and the byproduct are separated in this second distillation column. And so, looking at this, it looks complex, but taking your time, and I think that's one of the things I hope to emphasize in this class, looking at things step by step. A complex process like this just becomes a series of sequential material balances. And if you do things piece by piece, it becomes a lot easier to digest. And so, don't try to do everything all at once. Look at little pieces and answer the questions as they come. And here's some information for this process. You will not need all of it. You will need a good bit of it in terms of doing the material balances. Here are some of the assumptions associated with cost and energy, some data, heat capacities if you want to do math with it, the ideal gas equation for heat capacity, Antoine equations, heats of formation, all the stuff that we got for Google for you, so you didn't have to do the Googling. It's pre-Googled. And this is the actual assignment. And so what I'm wanting is just a quick 1-2 page report that goes over the process while answering the questions that we have here. And so, the key is, can you write an effective report that answers the questions provided while providing the necessary appendices to support what you've written. At the same time, you'll need to come up with an Excel stream table, which identifies the material balances for the process. So you'll have to do this for all streams, stream 1 through, I don't know how many are there, 20. And so basically you'll need the report, the Excel sheet while answering these questions. And it will be due at the end of the class on June 22nd. I'm not expecting you to be able to knock it out in a day, two, or a week, but that's one of those things. Take a look at it, see what you can do with it, see what questions about it you have, then come talk to me. I expect this to be kind of a back and forth type process. The earlier you get started, the less intensive it will be. If you wait till June 20th to get started, you're gonna have a bad time. So I would say this week, take a look at it, see what kind of thoughts, formulations you have, come up with some questions, and we can talk about it. And then probably by the end of next week, you should have a good amount of material balance information under your belt that you can start taking a good crack at the stream table, as well as beginning to answer the questions. Then probably by week 2, by week 3, you'll be finishing those questions. And then maybe that last week, all you have to do is write the report. And so I encourage you to take that type of approach instead of the seniors do tomorrow approach, just because that's not going to be very pleasant. And then I'm going to get lots of wonderful student evaluations that he gave me this big project and it took forever, and it's not going to help you. All right, any questions on this? I'm sure you will have more once you've had time to digest it. But this should be all you need in order to get started with it. And it, like I said, it serves as a really good reinforcement for all the principles that we're going to talk about in this class. Okay. All right. If there's no further questions, then for the next half hour or so, we can kind of do a quick run through of the review lecture that I've prepared, which is a review on chemical process variables, and touch briefly on the problem solving discussion that I have. So let me see the best way to do this. All right. So if you've toured Blackboard, you should see some of the lectures that I have already made available. This one being the first lecture, which is a review on process variables. All my lectures, I kind of have objectives, which is, things that I hope you get out of looking through the slides. In a typical lecture, I don't like talking at slides. I usually take notes using this notes. I've got a nice handy dandy pen, but in this format, it gets a little tricky to bounce between the two. So I'm gonna make this more of an informal preview of the slides / discussion. So if you have questions, feel free to stop me. If there's anything that you want, like, hey, can I get an example of that? Or, what's that helpful for? Or, you did that wrong. That happens a lot. I'd be more than happy to stop, correct myself, provide any clarification and things for you guys. Okay. So a lot of the things in terms of preview for this course is in just understanding key concepts, definitions, and variables associated with materials that we see, as well as chemical principles. So one of the big things that we look at is how do we quantify and qualify materials. Well, we have things like, mass, density, volume, as well as specific volume and specific gravity. So let's take a quick look at some of these and talk about it briefly. So when I, think of density, I can consider that simply, something's mass over its volume. But when I consider specific density, specific gravity, now I'm looking at the density of an object with regard to some reference material. And yes, I will apologize now, I don't have the best handwriting / artwork. It's an acquired taste. And you have to acquire it whether you want to or not. And so when I'm considering specific gravity, I have to consider, what's the density of a material with respect to a reference. For liquids, that reference density is water, which is 1,000 kilograms per cubic meter, 1 gram per cubic centimeter. And for those of you that will eventually be in fluids with me, 62.4 pound mass per cubic feet, because the English are fun. Now for gases, the reference is air, and air's density, it does vary with temperature pressure, but at standard temperature and pressure, it's about 1.29 kilograms per cubic meter. And I don't know the rest of the conversions. It'd be kind of like 1.29 times 10 to the minus 3 grams per cubic centimeters. And it's small in pound mass per cubic feet. We actually don't do that much. But the key things to consider is, what do these terms mean and why are they necessary? So looking at a quick example, if I have a liquid with a mass of 10 grams placed in a container and a volume measured is being about 20 cubic centimeters or 20 milliliters, depending on who you are, we can do a quick density calculation. And so, the density is what? When the mass is 10 grams and the volume is 20 cubic centimeters. And that quick math just indicates it's about 0.5 grams per cubic centimeter. However, if I wanted to know what's that density in pound mass per cubic feet, I would have to consider what are the conversions from grams to pound mass, and what are the conversions from cubic centimeters to cubic feet. So anybody know what the conversion is outside of the Google from grams to pound mass? You can unmute yourself. You might have been muted by default.
453.593 grams per 1 pound mass.
That's correct. So about 454 grams to 1 pound mass. Anybody? How about cubic centimeters to cubic feet? No? Well, I know there's 100 centimeters and 1 meter, and there's 3.28 feet in 1 meter. So I can use dimensional analysis to get from cubic centimeters to cubic feet by saying, all right, if I've got 1 centimeter and there's 100 centimeters in 1 meter, if I keep that, and then 1 meter, there's 3.28 feet. I can keep that, then I can get the conversion. Or you can take the inverse. And so, this emphasizes the importance of dimensional analysis and not necessarily knowing every conversion under the sun, but knowing how to go from one set of units to another. That becomes extremely important when you're looking at doing calculations with process variables. So going back to what I had earlier, I had 0.5 grams. Oh, that looks ugly. Per cubic centimeter. And I know we said 454 grams in 1 pound mass. And there's 100 centimeters in 1 meter. And in 1 meter, there's 3.28 feet. So what does that density now become? Doing a quick check of my units. Grams cancels, cubic centimeters cancels, cubic meters cancels, and so I'm left with pound mass per cubic feet. Anyone want to give me that? No? All right, well, let's see if I think I might have actually gotten this lecture solved out.
I think it might be 31.2.
All right, let's take a look. I did get 31.2 pound mass per cubic feet. All right. So let's keep rolling, going through some of these concepts. I already touched base on specific gravity, looking at densities in comparison to a reference. Another good concept is regard to flow rate, which is in concern when, especially for chemical engineers, when we're moving material via pipes, tubes, pipelines, we like to know what's the relative speed and flow rate of that material as it moves through our process. And so a flow rate could be measured in terms of mass per time or on a volume per time basis. And we often use density to convert from one to another. So looking at a quick example, if I have liquid toluene flowing through a pipe at about 175 cubic meters per hour, I can ask myself, well, what's that flow rate in terms of kilograms per minute? And how long would it take to fill a tank with 6,000 pound mass of toluene? So let's take a look at this example. As soon as my computer can work with us. Also, fair warning, my computer likes to crash when I take notes because it gets overheated because it's an ultrabook, which means really poor cooling. So fair warning, just bear with me. We'll do what we can. So we had a liquid flow rate of about 175 cubic meters per hour. And I want to know what's the mass flow rate in kilograms per minute. Well, I need to know the density of liquid toluene. So that's some information that I need. And if I don't state a temperature, pressure, and those kinds of things in which the liquid toluene is at, I'm going to need to make an assumption in regards to the temperature and pressure of that liquid toluene flowing through the pipe, which for most processes, we like to make an assumption that we have a standard temperature, the most common being 25 C, and a standard pressure, most common being about 1 atmosphere. So if I did a little digging in terms of that density, okay, it should be, according to what I've already calculated, about 867 kilograms per cubic meter. Now with the density, I can convert from a volumetric flow rate to a mass flow rate, because the mass flow rate is simply a volumetric flow rate times density. And so I have 175 cubic meters per minute. And if I multiply that, per hour. And if I multiply that times 867 kilograms per cubic meter, and then I can convert from hours to minute. 1 hour is 60 minutes. And then I can say, well, so what does that make my mass flow rate?
$25, $29 kilograms per minute.
2,529. That sounds about right. It's pretty high. All right, so that's booking. Well, all right, let's look at the last part of the problem. It asks, how long will it take to fill a tank with 6,000 pound mass of toluene? Well, we have our mass flow rate, and we have the total mass of the tank being 6,000 pound mass. Now, to find the time, we just simply need to take the total mass divided by the mass flow rate. But we can do one of two things. Since the total mass is in pound mass and our flow rate's in kilograms, we can either convert the kilograms to pound mass to do the calculation, or convert the pound mass to kilograms to do the calculation. Now, most of the time, it's usually a lot more beneficial to stay in SI units when you're doing calculations, unless you're doing fluids because they're weird. So we can go ahead and just do a unit conversion to get from pound mass to kilograms. Now, 2.2 pound masses, or pounds, is in 1 kilogram. So what is this conversion? So what's the total mass of that tank in kilograms?
The total mass is 2,727 kilograms.
Okay. 2727. So now we can find the time it takes to fill that by taking our 2727 kilogram tank and dividing by our flow rate, 2,529 kilograms per minute. So that should give us about 1.1 minutes approximately. One quick note here, since we're kind of getting into some calculations. I always, come up with that discussion on sig figs in terms of, what's a good number to use. My answer always is use what makes sense, meaning when you're doing calculations, especially now that we have nice software, just propagate the digits that are generated throughout your entire calculation. But when you report answers, report them in a way that makes sense. Which means most often than not, you're going to be looking at 2 to 4 sig figs max in a given situation. So for example, when I said, okay, what's the mass flow rate? If I had 175 cubic meters per hour of this toluene, and I asked, what's the mass flow rate? Well, saying 2,529 isn't really going to be, while accurate, it doesn't really help a whole lot. A more effective answer is about 2530, even, a little over 2,500 kilograms per minute. Because in the grand scheme of things, I'm not a sensor, so I don't really care a lot about the exact answer. Not to say, accuracy and precision isn't important, but like I said, this goes back to communication. And so, give me the answer that makes the most sense. At the same time here, this is a little over a minute, and the total mass a little over 2,700 kilograms. And so, like I said, use about 2 to 4 sig figs in most circumstances. All right, let's keep moving. All right, let's look at this next example. So suppose we have a gas flowing through a cone-shaped pipe. So how do the mass flow rates of the gas at the inlet and outlet compare? And how do the volumetric flow rates at these 2 points compare? And assuming if the gas density is constant and if the gas density decreases. So let's take a look at this. Let's talk together and see what we can come up with in this problem. So I've got a cone. It's got some material, mass flowing in, and some mass flowing out. So what can I say regarding the mass flow rate moving through this cone? And what I'm getting at is the mass flow rate going to change? Or I can also say, does the mass flow rate in equal the mass flow rate out? So is that a yes or a no or an I don't know or maybes only on Tuesdays? What do you guys think? You feel free to talk, to chat. You can, I don't know, do a emoji, whatever you guys like to do, hieroglyphics. This is getting a little messy. So what do you guys think?
The mass flow rate does not change.
Okay. I will agree and say, no, the mass flow doesn't change. And yes to this statement. So the mass flow rate does not change. All right, now let's take a look at that flow through this cone again and consider it in terms of the volumetric flow rate. If the volumetric flow rate is simply the mass flow rate divided by density, such that now I have the N equal to mass in over the density in, and the volumetric flow rate out is the mass flow rate out over the density out. How is my situation going to change? Can I say that my volumetric flow rate in equals my volumetric flow rate out if rho I, or the density is constant, or rho in equals rho out? Is that true or false? These are good quiz questions. Be like true, false, maybe, and I don't know, please, can I have partial credit? That's usually the choices I give. Well, in this case, if the densities are constant, I can state that my volumetric flow rate is not going to change, because I can put these systems together and say, you know, if mi over rho I equals mo over rho o, if I already stated that my mass flow rates are constant, and if my densities are constant, then this should hold fine. Now, the tricky part is if now I say the density decreases such that my initial density is higher than my output density, then this changes a little bit. And if my density initial, make sure I'm writing it consistently. is RO, then MI over rho I is going to be less than MO over rho O, right? If I assuming that my mass flow rates are going to be constant, right? That resulting sum, when I divide out my divisions, is going to cause these two values to not be equal. And that tells me that if my density decreases, my volumetric flow rate increases. Is there any questions on that example? Does it make sense? Do you buy it? Don't buy it? Need a coupon? I will take your stunned silence that you are all just amazed at this example. Or you just like being silent names on the Zoom call. All right, let's keep moving. All right, so we're running to the 11 o'clock hour. I don't mind going a little over, but if you have to get off, I completely understand. I won't deduct any points from Gryffindor. But if you're okay with me, I'm going to keep going. So, you know, a key process variable, temperature. It quantifies the intensity of molecular motion. The things I want you guys to be comfortable with is know the various temperature scales, how to convert between them, and understand the difference between a temperature degree as an absolute value and as a a temperature interval. A lot of times when looking at calculations, we consider things in terms of the intervals and the deltas, not necessarily the actual values. And so understand that, you know, 1 delta degree C is equivalent to 1 Kelvin, 1 delta degree Fahrenheit is equivalent to 1 delta degree Rankine. And then to convert from a delta degree F to a delta degree C, you multiply and or divide by 1.8, depending on which direction you're going. All right, I'm going to skip the example. All right, pressure is another big concept when we're looking at chemical processes as a variable. It's force per unit area. It's the force that the molecules will exert upon its surrounding environment. It's a tangential, it's a normal force that a material acts upon a surface. Understand the various units and ways that we describe pressure, the unit conversions. You know, we're all comfortable with an atmosphere. An atmosphere is 101,325,000 pascals, 14.7 psi. A bar is not an atmosphere, it's close. It's the like engineer's rounding version. It's just 100,000 pascals. And where possible, it's always nice to use SI units. So if you can get your pressure in pascals, it makes it a lot easier to do calculations. Gets a little tricky when you're doing things in English because you have to consider a gravitational correction constant, G sub C, to go from pound mass to pound force and back, and vice versa. One of the concepts that it's discussed in chapter 3 is hydrostatics, which discusses the relative pressure that exists as a function of depth and elevation in liquids and gases. So really quickly, you know, rocketing through hydrostatics or fluid statics. If I have a column of a fluid, it looks like this. Here we can make it blue because water. Okay. I got a column of liquid. The pressure at the top and the pressure at the bottom are not going to be equal, but I can determine the pressure at the bottom as a function of the pressure at the top by applying a fluid statics expression where that pressure varies as a function of density, gravity, and relative height, which just means the weight of the fluid causes an increase of pressure, right? Because it's just sitting on top of itself, which is why we see an increase of pressure as we move down a column of fluid. Good way that we measure it is using manometers, where we can look at relative heights to determine and measure pressure in various systems. The good news is we have the technology that we don't always have to rely on manometers. We can just use pressure sensors with digital readouts because much easier. But it's good practice. You can look at this system and see what you can do in terms of calculating the pressure at point A. One other thing that it's important to note is gases don't behave like liquids. And so when you consider hydrostatics of gases, it becomes a different expression. It's the barometric equation, where we don't have that simple rho GH expression. We have to consider ideal gas law, which we'll talk about more so in this class. When you consider that, the expression changes. We still have the relative pressure, but now we have to consider other values: molecular weight, ideal gas constant, absolute temperature. There's an example on this that we have here, looking at calculating the barometric pressure of a home in Denver, as well as in Pikes Peak. You can ignore that noise. It's just a weather radio. I apologize. Some more things I want to kind of touch base on as well. Moles and molecular weight. We're going to be spending a whole lot of time talking about molecular weights, average molecular weights of mixtures, the number of moles in a system, especially when we start looking at reactors and material balances involving reactions. But make sure you're comfortable with understanding how atomic weights are calculated, how to calculate molecular weights of components and compounds, and as well as the types of moles, how to convert from a gram mole to a pound mole to a kilogram mole, or a kilomole. And we could take a quick look at an example like this, looking at, let's say, the molecular weights of ammonia, octane, and caffeine. So what's this example? Sorry, wrong button. Ammonia. Right, so it's NH3. We have to say, okay, to find the molecular weight of this, there's one molecule of nitrogen. Nitrogen has a molecular weight of 14 grams per mole. Hydrogen, there's 3 molecules of hydrogen and has a molecular weight of 1 gram per mole. So this gives us a molecular weight for ammonia of 17 grams per mole. For octane, which is C8, H18, I believe. I gotta make sure I'm right. Okay. Molecular weight for octane, well, there's 8 molecules of carbon, which is 12 grams per mole, and there's 18 atoms of hydrogen at 1 gram per mole. So this gives us, let's see, 18 plus 96. 96 plus 18, which is 114 grams per mole. And then last but not least, caffeine, C8H10 N402. H10N402. To find the molecular weight of caffeine, we have 8 atoms of carbon, 12 grams per mole for each. 10 atoms of hydrogen, 1 gram per mole. 4 atoms of nitrogen at 14 grams per mole. And 2 atoms of oxygen at 16 grams per mole. Which gives us 96 plus 10 plus, what's 4 times 56 plus 32. And I got 106 and 88, which is 194 grams per mole. So that's how we can find the molecular weight of compounds outside of Google. Now, Google's going to give you a little bit different values because it's looking at the average molecular weight of all the isotopes of or associated with a compound. They're a little different. And with molecular weights, we can determine the number of moles based off of masses and substance, and we can move from a mass basis to a mole basis in most of our problems. For example, if I have 100 grams of CO2 and I wanted to know how many moles of CO2, well, I need the molecular weight of CO2 because I can move mass and the number of moles. Oh, well, my pen's being a little weird. The number of moles of a substance is its mass times over its molecular weight. And so if I have 100 grams, I need to know what's the molecular weight of CO2. But I can do the same type of calculation as I did above. And I have 1 atom of carbon to 2 atoms of oxygen, which gives me 32 plus 12, which is 44 grams per mole of CO2. So if I do that conversion, I'm left with 100 over 44, which is what example 8 gives me about 2.3 grams per mole, or 2.27 moles of CO2. Another important thing to understand when we're looking at mixtures with various compounds within the mixture, being able to understand and identify the mass fraction of a component in a mixture as well as the mole fraction. It's important to make sure you're looking at the right basis and knowing how to convert from a mass fraction and a mole fraction using molecular weights when appropriate. As well as, if you have a bunch of things in weight, looking at the average molecular weight based off of being given mass fractions and mole fractions. I think the last thing that this talks about is concentration. We'll talk a little bit about this tomorrow. One thing I did want to note, because I don't want to take too much of your time, is a quick discussion on problem solving. Now, I mentioned this at the beginning of class, that there's 2 ways in which a lot of people like to work out these kinds of problems. Is, you write the necessary equations you need, and you just kind of plug and chug it, get your solution, circle it, and move on. Or you can draw a flow chart for a problem, identify the information you have, the information you don't have. Do what's called a degree of freedom analysis, which we'll talk about tomorrow or the next day. Figure out the necessary steps to get to a good solution, and then you write out the necessary equations and solve. It's a lot faster to do the first approach, but as the problems get more complex, you'll find it's a lot more effective to look at and use the second approach. And so I wanted to take time to kind of let you know, beware of just trying to get through a problem too quickly for the sake of getting it done. Make sure you're using an effective strategy and good technique so that when the problems get complex or difficult, you don't get lost, you don't get unorganized and messy, and that's when things go south. So it's better to practice and build that good habit when the problems are simple, so that you have the habit in place when the problems are complex, versus when you're trying to, develop the habit while you're also trying to get through complex problems. All right, well, that's all I have for you guys today. Is there any questions, anything I can answer or address before we sign off for a little bit?
Do you know how long it'll take to upload the recorded lectures after a lecture?
About 20 minutes. These are pretty long videos, which means it'll take a little bit for me to compile them up, but I'll hope to have them up within the hour.
Okay, thank you.
Mm-hmm. You'll just have to bear with me and my computer. I don't have a nice, good video editing putting together. I just got this Surface, which, while nice, doesn't have the bandwidth to do a lot of multitasking in terms of compiling video.
How often do we use the PowerPoint? So is there a PowerPoint for every day we're going to come to class? Or do we, we're going to use this one for 2 days, use the next one for a few days?
It'll be more that method. We're going to use one for a couple days.
Okay.
Yeah, I think I've got 5 or 6 up right now, and that's about 10 to 12 days.
Okay.
Yeah. All right. If there's no more questions, I'm going to get off, guys. Thank you all for attending. I hope to see you in the next lecture, maybe a little more engaged. And I know everybody likes my voice, but I would really like to interact with you guys a little more, and hopefully we can have good discussions. So take care, guys. Stay safe, and I will see you maybe in office hours, or at least hopefully in the next lecture tomorrow. Have a great day.
Have a good day.
Have a great day.